Hello, I'm Eric, and for section 10, we're going to go over polynomial time reductions, the class of NP functions, NP completeness, and the Cook-Levin theorem. Now, this material is some of my favorite material of 121, but it can get really confusing, so let's get straight to the material. First up, some context. So we learned in previous weeks two classes of functions, p and xp, and we also learned how to use reductions and Rice's theorem to prove that certain functions are uncomputable. Now we want to revisit these reductions with the added notion of time complexity. And in future weeks, we'll talk more about more classes of functions and algorithms such as randomized algorithms. So first up, polynomial time reductions. As a reminder, we used reductions in the past to prove uncomputability by giving an algorithm to compute a function that everybody knew was uncomputable. And so the layout was primarily like this. If we wanted to prove that A reduces to B, we gave an algorithm that computes A using an algorithm that computes B. And specifically, this algorithm had to transform the inputs of A into the inputs of B using a function G. And we see on the right here, this is the new version of this reduction with the polynomial time reduction part added. So we see here that instead of the function G, we call it the function R. And we're stipulating that this function R must be computable in polynomial time. And of course, this adds another component to our correctness proof, and that we also have to show that R can be computed in polynomial time. You saw in class the formal definition of this, so I won't repeat it in detail, but we want to note that if you prove that a function f is polynomial time reduced to a function g and vice versa, then we say that f and g have equivalent complexity. And later on, we'll see that several problems and functions actually have equivalent complexity because you can essentially reduce both of them to each other in polynomial time. So why do we care? Why do we bring up this notion of polynomial time in terms of reductions? Well, it's because if we prove A reduces B in polynomial time, then that means if B can be computed with a polynomial time algorithm, then A is also computable in polytime. This is really useful to think about in the real world when we know we have an algorithm, for example, for B that is efficient in terms of it can be run in polynomial time, then we can also try to discover an algorithm for A that's also efficient. Note that we can't say this for the regular reduction A reduces B because with the function G up here, we saw that there's no guarantee that G runs efficiently. So when we're trying to kind of get the inputs of A to turn into the inputs of B, G might have been in the class of XP and not NP. And that means it'll take an exponential time for the inputs of G, for the inputs of A to be transformed into the inputs of B. So that brings us to a new class of functions, and we're calling this class of functions NP. And when people first learn about this class of functions, sometimes it's easy to mistake it to stand for not polynomial time. But I want to emphasize that this is not what it means. NP does not equal not polynomial time. Instead, it refers to non-deterministic polynomial time. And this is essential for you to remember because it's actually saying that this class of functions has a property that it can be verified in polynomial time. It is efficiently verifiable. And what's furthermore, NP does not equal polynomial time because all functions in the class of P actually lie also in the class of NP. And so all the polynomial time functions, all the functions that can be computed in polynomial time are also in the class of NP. That's very important to remember. So let's have a concept check. And to prove that the class function is NP is a subset of XP. To prove this, we can look at the definition again. And we realize that the definition of NP relies on this part, where we have a verifier, V sub F, takes in an input X and a certificate W, and this outputs 1 when X outputs 1 when it's input into the function F. So given that, we see that to discover an algorithm for every function in NP, let's say we have a function F in NP. To get an algorithm to compute it, all we have to do is check all the possible certificates W for every input X. And we see here that W is of length n to the A. And how many different possible strings are there possible for a string of length n to the A? Well, it's 2 to n to the A. And because we know A is a constant, then there's an order of magnitude of 2 to the n to the A, or exponential number of possible strings W can take. And thus, we can just loop over all the possible strings of W, and that gives an exponential time algorithm to compute F. And thus, F must be an XP. Knowing that, we can draw this pretty diagram where we have these different classes of functions. And you see that there are functions in each of these classes. And there's a dotted line between P and NP, where we have certain functions which we don't know either are NP or P. So you might notice in this visualization that, for example, halt is on the outside of all these different classes of functions, R, XP, NP, and P. And we say functions like halt are NP hard because all functions in NP can be reduced to it. In other words, for all G in the NP, G can be polynomial time reduced to F, or to halt in this case. And a second condition or concept is that NP completeness refers to a function F that's NP and NP, but is also NP hard. And this means that halt is not NP complete because it is not in the set of functions or class of functions NP. Instead, we'll later learn on in class or in section that 3-sat is NP complete because we know that 3-sat lies in NP, but it is also NP hard. This brings us to the Cook-Levin theorem. Again, from earlier on, we know that reductions are powerful because once we prove A polytime reduces to B, then we know B is an NP. If B is an NP, then A is also an NP. Furthermore, we know that if A is NP hard, then B is also NP hard. From the Cook-Levin theorem, we learned that 3-sat is NP complete, and I won't go over that whole proof again, just because you learned that in lecture. But the key concept here is that from the definition of the class of NP functions, we knew that with a given function f and an input x, we can use a verifier for f and get a small circuit C that correctly outputs 1 or 0 based on whether or not a certificate is correct proof for the input x. Now let's go over some example reductions. So the first example reduction I'll go over is a polytime reduction. And the second one is of a problem that may or may not be NP complete. So let's first go over zero-one linear equations. Now, zero-one linear equations, the problem, has a really long kind of name and might seem intimidating, but let's first read the definition of it. So we can see that a zero-one linear equations problem corresponds to a function zero-one EQ, where it takes input a collection E of linear equations with variables x sub 0 to x sub n minus 1, and outputs 1 if there exists an assignment for every variable of 0 and 1 values that satisfies all the equations. So in essence, it's referring to the systems of equations, such as this one and this one, and whether or not we can find an assignment for all these variables such that all the equations are satisfied. And really quickly, one satisfaction here is giving x sub 0 equals 0, x sub 1 equals 1, x sub 2 equals 1. Now, remember, this problem is not asking for us to actually find a satisfying assignment, but whether if a satisfying assignment exists, then it must output 1 and 0 otherwise. So the problem here is to show that there's no efficient polynomial time algorithm to compute this 0-1 EQ problem. Well, from what we learned earlier, we know that to show this, we have to reduce a NP-hard problem like 3-set to 0-1 EQ. So I have to do this. So what are the steps? Well, the steps for a polytime reduction proof is to first describe reduction function R to transform the inputs from 3-set to 0-1 EQ, and then show that R can be computed in polynomial time, and then we have to show that the function R and the algorithm is actually correct in terms of completeness and soundness. So let's go through the steps. Step 1 is that we want to convert the inputs of 3-set to 0-1 EQ. Recall that 3-set looks something like this, where we have clauses, and we want each clause to basically output 1 or compute to 1. And just like in 3-set and 0-1 EQ, in both cases, every variable can either be 0 or 1. And if you think about the problem of 3-set farther, we can actually see that each clause is basically a constraint on the variables. Because for example here, we know that if x equals 0 and x1 equals 0 and x2 equals 0 and x3 equals 0, then this clause would not be satisfied. This cannot happen. And so therefore there's some kind of constraint that each clause places on a group of variables. And that leads us to system linear equations. We see that if we write it in a different way, x1 plus x2 plus x3 has to be at least equal to 1, greater than or equal to 1, based on this 3-set clause. And similarly, we do the same for this clause x4, x5, x6. So we're almost there, but we have an inequality rather than equality. So to make this an equality, into an equality, we can add auxiliary variables. For example, adding y and z, where y and z are either 0 or 1. And then make it equal to 3. So we see that if x1, x2, x3 exactly equals 1, then y and z could both be 1, and that will make it equal to 3. Or if x1 plus x2 plus x3 equal 3, all of them are 1 in the beginning, then y and z could be 0, and this would still be 3. So this effectively transforms this inequality into equality. And we can do this for every single clause. Now, sometimes in 3-set, clauses can have variables, and not just x1, but it could have x1 bar or x1 prime. which refers to the negation of that variable x1. Now we can refer to this and translate it into 1 minus x1 in terms of the equation here. So that's another thing that we're defining. It's formally laid out. It means that our reduction algorithm R transforms every single clause of 3-set into this format, as we said below or above. Great. And another stipulation that we have to have is that xi and its negation xi prime must equal to 1. Remember that for all xi must either be 0 or 1. And so this enforces that if xi equals 1, that xi prime must equal to 0 and vice versa. Cool. So given our reduction algorithm R, we want to show that it runs polynomial time. And we go through the steps of how this might be implemented using pseudocode to transform these clauses. So the first step is to actually compute all of these things. So for all variables x sub I, we have to set up the constraint such that xi plus xi prime equals 1. And that'll take this n steps because we have n variables. And then we have another loop of m steps to take care of these m clauses and convert them into the equivalent equality. And then we're done. And remember that inside the loop, each iteration takes a constant amount of time to convert this clause into the equation. Now that we've shown that the reduction algorithm runs in poly time, we want to show that's correct with completeness and soundness. First off, in completeness, we show that if there's a satisfying assignment for 3-set, then there must be a satisfying assignment for 0,1 EQ as well. And we see this given our intuition from the function R. And we know this because if 3-set outputs 1 on some phi, then there is an assignment W to satisfy phi, such that for all the clauses, they all compute to 1. Then we can directly translate that into that all the inequalities here for the clauses are greater than or equal to 1. And because in our reduction algorithm, we add these auxiliary variables y and z, we know that if this inequality holds, then this equality must hold. And therefore, letting xi prime equals 1 minus xi, and then translating all of these clauses into their respective equations, we know that if 3-set is satisfied, then 0,1 EQ must also be satisfied. Now soundness goes in the other direction. So now we're supposing that 0,1 EQ has a satisfying assignment. We want to guarantee that 3-set also is satisfied. Well, in this case, we can again think about what happens when 0,1 EQ is satisfied. That means for all these system linear equations, we can find a satisfying assignment such that all of them are satisfied. Then with that, we know we have for each of these variables, x sub 0 through x sub n minus 1 and all the auxiliary variables, we know we have a satisfying assignment that either tells them it's 0 or 1 for each of them. Well, given this information, we can transform that back into the 3-set assignment. And we know that because in our way we set up our transformation R, x sub I prime is negation of x sub I, and all of our auxiliary variables are less than or equal to 2. And so that means, again, we have this inequality that must be satisfied if 0 and EQ is satisfied. Thus, it means that 3 set must be satisfied as well because of this inequality, because it directly translates into the clauses, that every clause must be satisfied. Awesome. Let's go over another example. This example, we're going to be working with cliques, and cliques are defined as a subset of an undirected graph where all the vertices are connected to one another. Mathematically, this means that if you have these vertices here, A, B, C, and D, they are a clique because you see that for every pairing of vertices, there's an edge connecting them. Now consider the function clique given a graph G and a number K. This outputs 1 if and only if the graph G has a clique of size at least K, which means that this set of vertices, the size of this set is at least K. Or else the function clique outputs 0. Now I want to see, is clique NP complete? Prove it or show why not. Well, let's consider how we will do this. So one way to do it is to prove that NP complete, we show the reduction, right? Reduction from an NP hard problem, we also have to show that clique is an NP. To show why not, that means we have to show there exists a polytime algorithm, compute clique. That would be the easiest way. Well, let's first kind of see how we can do this by reduction, because intuitively it seems like clique might be NP complete, and talk about why we might have the intuition soon. So the first part of showing NP completeness is showing that it is an NP. And again, remember this means verifiable polytime. Well, given a graph G, we see that we can verify if clique should output 1 or not if we have a certificate W, such as W is a set of vertices like this. And given this set, we can just check all the pairings of the vertices and see if there's an edge in between all of them. And because the combination of all these pairings is just based on the size of W, we just simply do a double for loop through this set of W, and we can verify in polynomial time. Cool, so that shows that clique is in NP. Now, the second part is showing that clique is NP hard. Well, we intuitively think that we can do this if we can reduce another NP hard problem to clique. Now, what are the other NP hard problems we learned in lecture and the textbook? Things like 3-stat, min-cut, independent set are all NP hard problems. And in this case, we think clique is NP hard because we see a lot of similarities between clique and independent set. And with that intuition, let's go into the actual proof. Again, here's a reminder for all the steps. Step 1 is to describe reduction function R to convert the inputs of independent set to inputs of clique. As a reminder, an independent set looks at a graph G and a number K and outputs 1 if only if the graph G contains an independent set of size, at least K. What this means is that with this graph G, it looks at for example, the set of three vertices, and it's an independent set if none of these vertices are connected to each other. So you see that A and D are not connected, A and C are not connected, and so on, all the pairings between these vertices. And so immediately you can see kind of these similarity between independent set and clique. And when we draw it out, we see that these two graphs seem really familiar or similar to each other. And we realize that for every single edge in the graph G prime, that edge is missing in G, and vice versa. For every edge, for example, between A and F here, we don't see an edge between AF and G prime. And thus we note that G prime is the complement of G. And so this points us in the direction of the correct reduction function, where we take a graph G and we return the complement of G, and then we also output the same K and input it into the clique function. So given that reduction R, let's show that it can actually be computed in polynomial time. And so there's two steps. One is actually taking in all the vertices and edges of G, and then we want to convert it to G prime, the complement. Well, how can we do this algorithmically? You can think about it, again, going through a for loop of all the vertices. First, we look at A, look at all its edges. If there's an edge between A and F, we delete it. And if there isn't an edge between A and B, we add it here. And so on for all neighbors of A. And then we move on to B and C and D and so on. So we see that it takes basically linear time to loop through all the vertices and edges of the graph G. And at each iteration, we're taking a constant amount of time to delete or add an edge. And so in total, it takes an order of magnitude of O of n plus m time. So given that we established it can be computed in poly time, I want to show it's complete. So first we show the direction that if there's an independent set of GK and G that of size at least K, then we guarantee that there's a clique and its complement. And so we can establish this by just looking at how we define the complement and how independent sets and cliques are defined. We notice that every independent set in G, let's say I subprime is an independent set in G, we notice that C subprime is a clique in G prime. Because when we converted G to G prime, when we converted to the complement, again, we deleted all the edges that were in G and also added all the edges that were not in G. That means because for every independent set in G, there were no edges connecting any of the vertices together. In G prime, we added all those edges together. And so therefore, that means that the same set I prime must become a clique in G prime. And given this, that means that if there exists an independent set of size at least K in G, that same independent set becomes a clique of size at least K in G prime. Therefore, this shows that this direction, and we showed completeness. Now let's look at soundness. Again, this is similar in its argument that if we see a clique of at least K, size K, in G prime, then there must be an independent set of at least K and G. How do we prove that? Again, we note that a clique in G prime gets transformed into an independent set in G. Why? Because a clique here, for example, the set of vertices, when we transform G prime into G, it was because, note that our reduction algorithm transformed G to G prime by getting the complement. That means that we added all of these edges. So for every edge here in G prime, we added. That means in G, none of these edges existed, and thus A, B, C, and D must have been an independent set in G if it was a clique in G prime. Therefore, if this is satisfied, then we show that there must also be an independent set of size at least K in the graph G. So what are the implications of all of this? Reminder that when we first learned about uncomputability and did all those reductions, we started from the halting problem, and then we went to all these other problems that we found were all uncomputable. And that was really powerful to see that certain functions and problems could never be computed. Well, we can do the same thing in terms of polytime reductions, in that we start with 3-set, and we learn that so many other things, for example, undirected Hamiltonian circuits, and the knapsack problem, and max cut, all these things can be related to reductions to be known as NP complete. And so we have this expanding web of problems that we all know are NP complete just because we can use polytime reductions. And also further note that a lot of these are discovered by Karp in 1972, where he wrote a paper with 21 reductions. And lastly, I want to quickly touch on what if P equals NP. This has been talked about for a long time in popular culture in terms of blogs or media. And people are claiming that if P was NP, then public key crypto will be broken, Bitcoin will be broken, you can automate discovery of mathematical proofs. But I want to note that this is not true necessarily, even if we prove P equals NP. Because if we only prove P equals NP in a kind of mathematical, non-constructive way, then we don't actually have discovered a fast algorithm for all the NP functions that we know of. Just because we know some fast algorithm exists for them doesn't mean we actually know how to implement them or whether or not they'd be fast enough. For example, the algorithm might take a polynomial time, but the constant might be some enormous number and still not be feasible to compute in a lifetime. And so that would not break public key crypto and so on. If you're interested in more of this discussion, I would recommend to check out these following videos. They're podcasts with some famous theoretical computer scientists, Richard Karp, Don Knuth, when they talk about the implications of P equals NP. The following are some more problems for you to practice on. Reductions and NP completeness is a topic where it's hard to grasp your mind around it for the first time when you learn it. And so I recommend to keep practicing. Thank you.